So the RADx-rad program supports innovative and non-traditional approaches to address COVID testing gaps and surveillance gaps. Specifically, we're interested in new methods to identify SARS-CoV-2 and its variants. And to do that, we have created a viral assurance quality panel so we can benchmark new methods against SARS-CoV-2, its variants, as well as cross-reactivity with other viruses. So here's kind of our dashboard here. So there were a total of 50 projects. For 44 of them, we have received data sets, and we may receive a few more over the next few months. Now, the development was really about developing, new types of technologies and making them commercially available. And that included a total 23 meetings with the FDA to discuss, specifics to get those devices approved. And that resulted in the submission of 7 pre and 1 emergency use authorization. It resulted in about 20 patents so far, 250 publications, and 1,800 citations. And to represent the special data in this project, we developed about 900 what we call tier 2 common data elements. So here are some examples. Here you can see the number of publications by the different sub-projects here. The Prevail Kids project is the one that was looking at MIS-C and was the wastewater project. Those were the biggest projects. They also have the most number of publications. And on the right side, you see the number of citations, and that is still growing, and we'll update that on a periodic basis. So the RADx-rad program is somewhat different from the other programs in that it's very diverse. And it can be grouped into 3 major research areas. One is wastewater-based surveillance. There are 7 projects there. The next one is multi-system inflammatory syndrome in children, or MIS-C. There are 8 projects there. But the bulk of projects are in new diagnostic methods development, and there are 35 projects. And now I will give you an overview of the kind of data we have in those various programs. So for wastewater-based surveillance, here are some of the research topics that were addressed. Tracking variants across the US, optimizing wastewater surveillance based on the settings, or if it's urban, rural, tribal, or university. Enhanced surveillance by developing advanced technologies and standards, as well as detecting multiple pathogens in a single wastewater sample. So for MIS-C, some of the topics were AI-based methods to predict the risks, severity, and outcomes in pediatric SARS-CoV-2 patients, the identification and validation of biomarkers, and the development of decision support tools, for example, to distinguish between MIS-C and Kawasaki disease. So for diagnostic methods development, we have a total of 6 topics. Here are the first 3. Development of electronic nose technology, and that's detection of COVID-19 through VOCs, volatile organic compounds. Chemosensory testing, those are at-home tests for taste and smell to detect olfactory misfunction or chemosensory loss. And then we have exosome-based technologies, which is a microfluidic technology to detect SARS-CoV-2 antibodies and other pathogens. So novel biosensing develops home-based diagnostics and breathalyzers. The automatic detection and tracing program was mostly focused on new sensors like electrochemical sensors, touch-based detection, or mechanical detection, as well as aerosol virus detection. And finally, the multimodal surveillance project used data from multiple data sources, including smart technologies such as smart masks, and it was applied to multiple populations such as dialysis patients. So that was an overview of the types of projects. As you see, they're very diverse. This shows how we organized data for the diagnostic methods development project. So if you look at the rectangular boxes, those are data files. And the boxes with the squiggly line, those are the associated data dictionaries. So it starts with the technology description, which has all the metadata about a technology project. You know, what are the biorecognition elements, what instruments were used, et cetera, et cetera. So we kept careful track of all the details of the new technology. That technology was then applied to clinical samples. And the description of clinical samples included minimum CDEs, which include demographics as well as medical history of patients, plus additional clinical data such as PCR data, vaccination data, and so forth. Then the technology was applied to those clinical samples that resulted in test results. And then based on the test results, clinical performance metrics such as sensitivity, specificity, etc., were calculated so we can compare the different methods. Now, to do those type of benchmarks more quantitatively, we created what is called the viral quality assurance panels. Those are inactivated virus panels where we know the exact concentration of the viruses. We know exactly which variant it is. Those inactivated viruses are then mixed, let's say, with saliva, and that creates spiked samples. Then the spiked samples are run through that same technology. You get test results, and from that we calculate analytical performance metrics such as the limit of detection. The common data elements that are being used here, both tier 2 and tier 1, they are available on the Git repository mentioned on the bottom right here. So this shows some details about how we benchmark diagnostic methods. We developed those inactivated virus panels, first for SARS-CoV-2 and its variants, and you see a lot of the Omicron variants are listed there. But we also want to make sure that the diagnostic methods are specific for SARS-CoV-2 and we don't get false positives. So we also had other common respiratory viruses such as human coronavirus, RSV, and influenza, so to look at co-reactivity. So one challenge with our project was, since it was so diverse, and there's no technology that's similar to any other technology, but we want to make sure that our data elements are kind of semantically similar. So here you see 3 different technologies. They use 3 different ways to capture the virus. One is using an ACE2 receptor. The second one uses a DNA aptamer, and the third one uses a monoclonal antibody. In terms of the data harmonization, you can see that semantically, they're represented in the same way. We have capture receptors, aptamers, antibodies. So we try to generalize those kind of concepts across technologies to make it more easily comparable. But then we also had to develop specialized data elements, and shown in this green color here. They're very specific for one particular technology. So the NIH Data Hub contains the data sets that are shown here in this diagram in orange. Those are data sets, and we know who created those data sets. But we wanted to provide more context. So we have all the publication related to those studies. We know all the citations to those primary citations. We capture presentations done through this project, as well as the patent applications for this project as well. So you can explore those digital assets using that link on this webpage here. Next slide, please. And those are a number of patents filed here. The Novel Biosensing Project filed the most patents because those were several SBIR grants, so they definitely want to protect their IP. So quite a number of patents were filed, and we will update this patent list as we go on. If you want to see any details on the bottom of the slides, there are links so you can check out what those patents or publications are and so forth. Next slide. So here are just some example how the data have been used from the project here. So those blue circles, those represent various RADx grants, and in yellow, those are principal investigators. And in the first example, two PIs collaborated. They put their data together and published a multi-site study by combining their data. In the bottom part, you see a joint patent application where two different projects, two different PIs worked together, used their data to file a patent application. So here are some examples how RADx-rad data sets are currently being used. So on the left-hand side in orange, we see two data sets from Miss C, and we see a couple of data users that are currently using those data sets for more detailed analysis. On the top right, we see an example of a data set usage that's related to the management of COVID-19 in dialysis facilities. And on the bottom right, we see another project that is about wireless COVID monitoring. So we hope we will see more of you, using those available data sets.
To find, access, and begin analyzing studies from this and other RADx data programs, navigate to the NIH RADx Data Hub at radxdatahub.nih.gov. Navigate to the Study Explorer, where you can use filters or text-based search to find studies of interest. The RADx Data Program filter allows you to filter studies by RADx Data Program. Once you find a study or studies of interest, click the study name to navigate to the study overview page. Then click the dbGaP study accession link to navigate to dbGaP to submit a data access request. It is important to note that the email you use for dbGaP must match the email you use for your RADx Data Hub account. Once you receive an email notifying you that data access has been granted, log in to the RADx Data Hub and navigate to the My Approved Data tab underneath Data Access. To learn more about how to use the RADx Data Hub, visit our helpful information page on the website, view our other videos, including our Getting Started playlist, or contact us at radx-datahub@nih.gov.